Chapter 10, slides 1 through 10. Okay, there's a warning here. Please do not continue with this chapter until you've gotten some handle on chapter 9. So I'm going to warn you right now that before you head into this, I hope that you've had ample practice with chapter 9. There's some good and bad news to that. There's going to be a lot of reactions in this chapter, not as many as the chapter 9. However, most of them can be managed and, really learned and taken in if you've mastered chapter 9, because a lot of the same mechanisms are going to be used here. There's going to be a lot of repeat reagents and repeat mechanisms. So that's the good news. Let's start with a little overview for alkynes. We're going to again use the pi bond as our nucleophile, and we're going to attack some reagent that is going to serve as our electrophile, just like we saw in alkenes. So the general reaction we're going to see is that both pi bonds are going to break. Because remember, an alkyne has a pi bond, and then the third one is the sigma bond. So it's a very electron-rich system between those two carbons. There's a lot of electron density between those carbon 1 and carbon 2. Let's number the carbons here so you can remind yourself that there are 4 carbons in the molecule drawn. We draw it like this without the bend. So alkynes are the exception to the ends and bends rule. Please don't draw your alkynes like this. Right? That looks bad to my eyes because the hybridization for these carbons are both sp, and sp is linear. Therefore, it is not good to draw your alkyne like this. It just hurts my eyes from a geometry perspective. So I've drawn it here, but sometimes students will miss the fact that there is a carbon 2 and a carbon 3. They only count the ends, but you got to understand there are 4 carbons to this system. So we've got a very electron-rich area between carbon 2 and carbon 3. And these electrons, like I said, just like the alkenes, will be serving as our nucleophile. And there is a lot of open space given this linear geometry, right? So it's a fairly open area. It's very exposed. So as a nucleophile, you don't have to worry about these very long rod type carbon systems because they don't have a lot of steric hindrance to them. So we're also going to look at these electrons, these nucleophile base scenarios, where these systems can both act as a nucleophile and or as a base. What does it look like? What does an alkyne look like from an orbital perspective? Well, I'm not going to try and draw it for you. I think it's best if we just look at some really nice images of these. And you can see at the top, the orange orbitals, those are the sp orbitals. Carbon 2, or 1 in this case, and carbon 2, are each using an sp hybrid orbital to overlap and form that sigma bond. Then the first double bond or pi bond that you're going to use is going to use a non-hybridized p orbital. Let's say that those are the ones in blue. They're using p orbitals. Well, we're already sharing and overlapping those parallel p orbitals to make the pi bond, right? The pi bond uses those unhybridized p orbitals. So the second pi bond has to be in the other trajectory. So just remember, we're using the x trajectory, carbon-carbon, to overlay our sigma bond. And then the pi system, the first pi bond is made, we'll say, in the y trajectory. And the last one, the purple one, must be non-hybridized p orbitals in the z plane. So you can see how we've used up all of the coordinates to make our pi system. You're never going to see a carbon-carbon quadruple bond because there's no more coordinate areas for the electrons to be shared across. It's just not allowed. So you can see that all of this electron density around the carbon is going to serve as a very non-sterically hindered, electron-rich nucleophile for our reactions. Okay, well, how do we name alkynes? Just a little bit on IUPAC naming. We did that with alkenes. The ending for an alkyne is YNE. And so it's just important to note that alcohols and alkenes are given higher priority than alkynes. And I'll just very simply start with the first one. I'm going to start my numbering over on the left. 1, 2, 3, 4, 5, 6, 7. Hept. That's my longest parent chain. There is a 2-methyl and a 6-bromo. And I chose to number from the left, putting the alkyne closest to the end, right? I wanted to get to my alkyne quickly. So the alkyne is at carbon 3. So you could write 3-heptyne, or you could write hept 3-ine. Doesn't really matter to me. And then we just put it all together. Now, here's some good news. There is no such thing as an E or a Z or a cis or a trans triple bond, right? Because it's linear. So you don't have to worry about any other further nomenclature. Put it all together, we have to consider alphabetical order. So we're going to say 6-bromo, 2-methyl, 3-heptyne. I'll leave the remaining 2 for you to practice on your own. Now, what about properties of alkynes? Well, again, we're not really seeing anything very different from the alkenes and the alkanes. On the whole, alkynes are very similar to alkanes and alkenes, again, because you've just got carbons and hydrogens, right? If all you have are, an alkyne, no other functionality, as a functional group, it's not very polar. So it's not really going to increase melting points and boiling points. Why? Alkynes have, on their own, there's really no hydrogen bonding opportunities. And there's really no polarity, right? There's no strong polarity or dipole attributed to them. So therefore, they're very similar to alkanes and alkenes. And if that's all you have in your system as an alkyne, it's not going to be a very high melting point or boiling point. Okay, so why do they deserve their own chapter? Well, they do have some things that alkenes can't do, and definitely more things than alkynes due to the electron density of the pi bonds. But what alkynes also have is the opportunity to become deprotonated. So I want to talk about the fact that what I just drew up here is an internal alkyne. What does that mean? Well, it means that on either side of the carbons, so if you have carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, a nonine. Okay, this is an internal nonine alkyne. Why? Because if you look at the 3,4 alkyne, there's a carbon on the left and a carbon on the right. So it's flanked by carbons. So internal alkyne versus an external or terminal alkyne. It can be written like this, or it could just be written like this. These are terminal alkynes. Again, we can assume the hydrogen, so it's not always drawn. I like to draw them in, but it technically is on a carbon, so you don't have to draw it. And these terminal alkynes have a little something extra that we didn't see with alkenes and alkanes. And let's take a look at what that is. This has to do with the acidity of the alkyne. So remember that if you had just a straight chain alkane, the hydrogen on one of those sp3 carbons, right? One of these hydrogens is sp3 in nature. So when it's removed, you have a negative charge on an sp3 carbon. Versus if you had an alkene and you removed one of the vinyl hydrogens, you would have the negative charge at a vinyl position, that is sp2. Well, if you remove one of the hydrogens on the terminal alkyne, then you would have a negative charge on an sp carbon. So let's go through it. A pKa for an alkane having an sp3 orbital lone pair is about 50. The pKa for a vinyl anion, the lone pair in an sp2 orbital, is about 40 to 45. And we talked about how that's not really that acidic. Here's the kicker. When you deprotonate an alkyne, because the electrons, you've dumped the electrons from the bond, you've dumped it into an sp orbital, that carbon with an sp hybridization. Do you know what the alkyne pKa is? It's around 26, 25, 26. Remember what water is? It's 15.7. Oh my gosh, that is a massive jump in pKa. So what this does for us is it shows us that these alkynes that are terminal have a proton on the end that could potentially be removed. So I'm going to come back to this point when we start talking about some chemistry. So hold on to that. But this is a property that's going to become very useful to us. As with every chapter, when you introduce a new functional group, it's nice to know and reflect on ways that we can make that functional group. Now, we haven't formally seen how to make an alkyne, but don't worry, you have the mechanism that you're going to need. What mechanism do we know that makes new pi bonds? If you said elimination, you are correct. And what we're going to focus on is E2. So we could use some very severe conditions, some really strong bases, and we need two equivalents to do this because we're going to do the E2 2 times, right? First time makes an alkene, second time makes the alkyne. How does this happen? Well, let's just look at an example here. Okay, we want to form the double bond in the more substituted position. We've got some heat in there. We're going to use sodium amide, which is an ionic, very strong base. And we're going to go after one of the hydrogens in an E2. This is the first E2. Did it matter which one I eliminated first? Nope. And then we do it again, the second E2. Strong base. Eliminates again. And we form our alkyne. Now it's this second base elimination that requires the use of NaNH2. It's why it's better to use this base, particularly because it's very difficult to remove the vinyl proton under these conditions. It's actually a little easier to do the first one, and the reason being is that the electron withdrawing group assists with that. But in the second case, we've lost that electron withdrawing group closest to the hydrogen, so it's a little tough to pull that alkyne, that vinyl hydrogen off. But ultimately, with some heat to overcome a very high energy, we can use a strong base and do a double E2 elimination to afford an alkyne. What if the halogens, right, the bromine, let's say, were on the same carbon? Could we still do it with two equivalents of the strong base? And the answer is yes. The negative nitrogen can do the E2 either way. You end up at the same spot. And then again, another equivalent of NaNH2. Does the elimination and gets you to the same product. How do you name it? Well, in this case, you've got 1, 2, 3, 4 carbons. This is 2-butyne. Okay, how about this? This is our first example of a synthesis question. What if I started with this Z alkene? How could I make the alkyne? Whenever I'm faced with a synthesis problem, I always count my carbons, right? Am I adding carbons, getting rid of carbons? What's the deal? So if you start numbering 1, 2, 3, 4, and then you count your carbons in the product, 1, 2, 3, 4, you can see that you're not adding any carbons. What you're doing is you're manipulating the functional group, the alkene. How do we do this? Well, I'm going to give you a hint, and there's going to be some practice at the end of this chapter 10, talking a little bit more about this concept. It's called retrosynthesis. And retrosynthesis is taking the product that you're interested in and working backwards, given what you know. So it might go like this. Ooh, I want to make an alkyne. How do I know how to make alkynes? The only way I know how to make alkynes is through a double elimination, right? 2 equivalents of NaNH2. And that is going to have to come from, I don't know, maybe something like this. 2 bromines, right? If I do 2 equivalents of the base, I would have started with the butane molecule, but I have to have those leaving groups there. Do I know how to put 2 bromines across 2 carbon systems? Taking a double bond and adding 2 bromines across, I do know how to do that. I just do a bromination with no solvent that can react, like water or ethanol. So sometimes it's helpful to move backwards than it is to move forwards. So now you guys have, using some chemistry that we've already considered, you have a way to put 2 bromines across 2 carbons by bromination. And then you have the power to just do your double elimination through E2 chemistry. Okay. We're now at the end of, chapter 10 is our last chapter for this semester. And this is organic chemistry. And I want to think about making new carbon-carbon single bonds. I want to, take 1 carbon and connect it to another carbon for the first time using a single bond, a sigma bond. How many reactions so far have we learned where we make new carbon-carbon sigma bonds? Again, we know how to make new carbon-carbon pi bonds, right, through elimination. But that's a pi bond. That's a new pi bond. How do I make a new sigma bond between 2 carbons? I mean, this is organic chemistry, right? I need to make carbon-carbon bonds and design big infrastructure for skeletal units of carbon. How do I do that? Let's think back. We covered a lot of reactions in alkenes. Is there anything there? Did we make any? Nope. Wow, nope. All of these reactions and we didn't make any carbon-carbon bonds that were new? It's like carbon-oxygen, carbon-hydrogen, carbon-oxygen, carbon-halogen. Oh my gosh. Made a lot of new sigma bonds, but they weren't with carbon. How about the next explosion chart page that I'd had? Oh, here's one. We made a cyclopropane. Woohoo! But cyclopropanes aren't that stable, you know, and they're you see them from time to time, but okay, that was the only one that we learned. That's really kind of crazy when you look back on it. We didn't really make a lot of new carbon-carbon bonds. Well, okay, so what kind of bonds have we been making? So if you think about the nucleophiles to date, the most common ones that we've been working on have been things like, you know, O-, methoxy, or, you know, ethoxy, you know, and they'll have a counter ion like lithium or sodium or potassium, right? Or lithium or potassium, whatever. T-butoxide, we use that one as a base. Okay, I mean, we've been using O-. Sometimes we had, you know, a sulfur minus, maybe that had a sodium counter ion. I mean, it's been heteroatoms for the most part, right? O-, S-, N-. It's like, okay, not enticing to give us the new carbon-carbon bond. So let's think about this. If I make a new carbon-carbon bond, one carbon has to be partially positive and one has to be partially negative. So I'm kind of failing on the partial negative carbon side, but there's good news. I'm not failing on the partial positive side. Let's think about SN1 and SN2. Okay, we had a nucleophile, albeit an O- or an S- or something like that, but understand that we were attacking very often an alkyl halide, right? The X was partially negative, but you know what? That's what made the carbon partially positive. Aha! I have found a common electrophile where it's carbon that's partially positive. So we know about those. We know about partially positive carbons, right? We've been using alkyl halides for chapters now. Now, we have seen some other ones. Maybe it wasn't as obvious, but remember, epoxides. Epoxides had a dipole. We had two partially positive carbons that we could make bonds with. Okay. So pretty familiar stuff here. Okay. I'm going to add one more to common electrophiles, and we're going to use it in this chapter. A carbonyl. Carbonyl has a strong dipole, making the carbon partially positive because the oxygen vector dipole-wise additive in one unified direction makes it a very electropositive carbon. So let's highlight these carbons. Partially positive, two partially positives, one partially positive. Partially positive carbons. Okay, our common nucleophiles, though, they're not typically the carbon minuses I was looking for. So I am going to keep this whole thing in my brain. I'm searching for carbons that are partially negative, right, or negative. And so where have I learned about carbon minuses? Well, not really that much, other than, we're going to take this guy, and we're going to consider the alkyne, the deprotonated alkyne, to be one of our first carbon minuses that we can use to do some chemistry, right? Because we just said that as long as your alkyne is terminal, if there's a proton there, I actually could add a base that was strong enough to deprotonate it, and that's going to give me my carbon minus. Now I could possibly do some carbon-carbon bond chemistry. So we're going to use this little framework here of common carbon electrophiles and common carbon nucleophiles when we're learning new chemistry from here forward. So let's do a few examples. Let's make some carbon-carbon bonds for a change, shall we? Let's take a terminal alkyne. Let's do some acid-base chemistry. I'm going to add a strong base, and I've given you the ones that you need to use. You can't use NaOH. I would like you to try down here why NaOH will not work. I mean, NaOH is a base, right? Well, let's figure out, using what we know, if this could work. What we'd want is the base to remove a proton. This is what we want. We want it to deprotonate, and then that would give us water. Counterion coordinates to the negative charge. So if this were to happen, because this is my desired, right? What I do is I look at the acid on the left. The acid on the left is the alkyne, and we said the pKa was about 25 to 26. And then the acid on the right, the conjugate acid, is the water, and we know the pKa is about 15.7. Which one is the weaker acid? Well, by about 10 units, the alkyne is the weaker acid. And we know that equilibrium favors the weaker acid. And that's 10 pKa units. That's a lot, right? Remember, it's almost unidirectional in the other direction, which means that this reaction will not happen. It'll sit as the starting material. Therefore, I know that this reaction can't use sodium hydroxide to deprotonate an alkyne, which is good to know. I mean, an alkyne, even if it's terminal, is safe under NaOH conditions. It's not going to get deprotonated. What if we change this to NaNH2? Well, now that's still, the alkyne is still the acid on the left, 25, 26, but now we've made NH3, and NH3's pKa is about 35. Aha! The weaker acid is now the ammonia to a large degree, and it will actually give me my deprotonated product and prefer to sit over on the right. So I've just proved to myself why I had to use these particular bases. I'm going to use these from henceforward when I'm trying to deprotonate my alkyne. Okay, so let's do that. NaNH2 is going to do some acid-base chemistry. I made my carbon minus. This carbon right here is minus, right? It has a lone pair now. And then I just want to do something with it, right? So why don't you throw something in there so that my new carbon minus can do something. So in the next step, I'm going to introduce, I don't know, 1-chloropropane, for instance. What's this mechanism? Strong nucleophile, in and out. SN2. Carbon, let's number 1, 2, 3. 1, 2, 3. 4, 5, 6. 3 is attached to 4. 4 is attached to 5. 5 is attached to 6. The chlorine got kicked out. The counter ion is the sodium plus. This salt is your byproduct, but what I'm interested in is this new and improved, bigger, better carbon product. Let's do it again. Take your alkyne. It's terminal. Introduce a strong base and do some acid-base chemistry. Deprotonate the alkyne. Make your strong carbon nucleophile. And then introduce an electrophile. I'm going to number here. 1, 2. Carbon with the lone pair is 3. This case, I'm introducing this epoxide. Oh, epoxides have 2 carbons that are electrophilic. I have to think about what conditions I'm under. Those blue carbons are partially positive. Who's in charge? Carbon 3 is in charge. When carbon 3 is in charge, when the negative is in charge, you're under strong nucleophilic conditions. We're thinking SN2. I got to avoid steric hindrance. So I'm going to number these carbons, 4, 5, and 6. And I'm really choosing between 5 and 6. 6 is less sterically hindered, so I am going to make a bond with carbon 6, opening up the epoxide and relieving it of its strain. O minus, carbon 4, carbon 5. Carbon 6 is now attached to carbon 3, which is still triple bonded to carbon 2, which is bonded to carbon 1. I'm done with the reaction. I was under basic conditions, so I'm probably going to work it up with some acid so that I can do some acid-base chemistry and satisfy that oxygen. So my final product here, 1, 2, 3, 6, 5, 4. Just trying to keep track of my carbons. I didn't want to drop one accidentally in the process. Woo, I've made this kind of complex molecule, right? It's got 2 functional groups I can do some chemistry with. This is exciting. Can we do one more? I mean, after all, we've just made a carbon minus. Let's introduce it to each one of these electrophiles. Let's go for the gold. Ooh, I spy with my little eye a new mechanism. Don't worry, folks, this is a preview to semester 2 for organic. We're going to be doing 1-2 additions, and I promise 1-2 additions will become very boring. I call them the in-up mechanism. I'll keep it simple for now, but get you comfortable with the process. No worries, it'll be one of your favorite mechanisms, trust me. NaNH2. Acid-base chemistry. Remove the terminal proton, gives us the carbon with the lone pair, negative. There's my nucleophile. And in this case, I am adding an aldehyde. Don't have to worry about regioselectivity. There's only one electrophilic carbon to attack. So let's do that. Take these electrons, make a bond, break the weakest bond. So as this bond is being formed, what bond must break? Well, it's the pi bond. Let's number our carbons. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. 3 is now attached to 4. 4 is still attached to 5. 4 still has one bond to an oxygen which gained the electrons and is now negatively charged. Okay, I'm done. And so I'm going to work it up, just like I did with the epoxide, under a little bit of acidic conditions to quench that negative charge, right? That oxygen is going to grab a proton from the workup, and I end up with, in this case, another alcohol, but the proximity of the alcohol to the alkyne is closer because I reacted it with the carbonyl. Let's double count. 1, 2, 3, 4, 5. Good. And 4 should have the alcohol, and 2 and 3 should have the alkyne. Just do a little double check to make sure I pushed my electrons and kept all the carbons from start to finish. Nice stuff. We've now looked at 3 different carbon-carbon bond-forming reactions using acid-base chemistry and changing up the electrophile. You guys have a lot of power.